Hi, this is a short two-part video demonstrating Kubernetes networking features available on both Windows and Linux today. The first part will give you an overview of the setup that I'm using, whereas the second part will show these features in action. To showcase these features, I've created a canal cluster, which employs a Flannelhost gateway backend for network management and routing between nodes. I combined that with the Calico Felix daemon that runs on each node and is used for network policy enforcement. Throughout the video, I will try to keep things concise, meaning I assume you know the basics of Kubernetes. Let's get started with an infrastructure and networking overview of the Kubernetes cluster that I'll use later in my demo. I'll start out very simple here and add more details as we go along. My cluster consists of 3 machines or nodes, each represented by one of these rectangles. I also have a physical network that you see listed below. My nodes are connected to that network with the following IPs assigned. In terms of operating systems, 2 of these VMs are Ubuntu based and one is running a recent Windows Server 2019 insider build. By attaching these VMs to my network, they were assigned a network adapter or a NIC. In terms of Kubernetes, the first Linux node you see here is the master, and the other 2 are my worker nodes that will be targeted for running my workloads. As part of Kubernetes cluster initialization, I also defined a cluster sitter 10.244. This lives in the routable address space and is used to assign IPs to all pods in the cluster, such that any given pod can communicate to all the other pods without requiring any network address translation. Every node feeds from this cluster sitter to request a smaller /24 subnet that's used for pods or containers scheduled on it. Each one of these /24 subnetworks on Linux CNI0 or on Windows CBR0 is created using either Linux bridging technology or is connected to a Hyper-V virtual switch on Windows. In each subnetwork, every pod receives its own VNIC with a unique IP address. Finally, any inbound or outbound pod traffic flows will have to pass through IP tables rules on Linux or its Windows equivalent called Virtual Filtering Platform, or VFP. VFP is responsible for programming rules for each container port based on things such as network security ACLs or any desired NAT operations used for egress or load balancing. Finally, there is one other network that I specified during initialization. It lives in this completely virtualized world. To explain what it does, let's take a look at the pod cluster network we defined earlier. This new network is called the service network, and it's a purely virtual subnet used by pods to access services. To be more specific, the service network is a set of virtual IPs, or VIPs, maintained by a controller manager. Anytime there is network traffic destined to go to a service VIP, kubeproxy will call into HNS to intercept the traffic and load balance it. This is done using DNAT operations across our backend pod IPs on the cluster network. Here's a quick overview of all the different subnets in my cluster, color-coded again. This concludes the infrastructure and networking overview. Next up is the second part of the video, which will demonstrate some popular Kubernetes features available today. For the first demo, I will define a service that will load balance across multiple pods. Here's a sample manifest that shows load balancing across multiple pods in action. What you see here is a service definition of type node port that exposes port 80. It points or load balances across a deployment consisting of 2 pods that use the Microsoft Windows Server core image for my specific Windows build. Let's take a look at this YAML file deployed on my cluster. So what you see here is a basic service VIP that's pointing to a Win web server deployment consisting of 2 pods with the .164 and .163 IPs assigned. If we try to curl the service VIP, it should load balance across these different IPs that you see here. So let's try that out. So what I'm running now is I'm curling the service VIP each second, and you can see that the IP address is changing each time we curl it. Now that's because we're load balancing across the backend pod dubs, as I explained earlier. There is a way to manually scale the number of pods in a deployment as well. Let's say we wanted to add another pod. We could do that as follows. This can also be done automatically using a horizontal pod autoscaler, which will also be available with Windows Server GA on Kubernetes. Here we can see another pod that has been added to my cluster. For the second demo, I will define example Windows and Linux services, as well as show how to communicate between them. Here's a sample manifest that defines Linux and Windows services. To keep things simple and demonstrate the different communication paths, I've defined some simple Hello World style services on both Linux and Windows. So the first one is called Who Am I and will be scheduled on Windows. The second one is our previous WinWebServer example. And finally, the third service is another WinWebServer example that I creatively called WinWebServer 2. I will show the different ways to access them next. Let's take a look at some of the different ways to access services scheduled across our cluster. Here you can see the 3 different services deployed on my cluster with all the pods running. In this window, let's try and connect to one of the Windows pods. Okay, I'm now inside the Windows pod. Let's try and connect to another pod via pod IP. Okay, great, that works. Let's try and connect via service IP. Let's pick this guy. Great, also works. Another way to access services is also by their name. Finally, since we define services of type node port, we can also try and curl them using that. So the node port will expose ports on each one of the hosts. Let's try the master IP. And let's target our Linux service. So as we can see, that worked as well. So those are all the different ways you can access services. Whether they are Linux-based or Windows-based, it should all curl the same way. For the third demo, I will show how to isolate Windows pods using the Kubernetes Network Policy API. Now, before I get to that demo, I wanted to give a quick conceptual overview, as well as convey the motivations behind network policies. Network policies are sets of conditions or constraints that allow you to designate who is authorized to connect to a given resource. Now, since defining network policies can be a bit of a dry topic with having to define either complex or repetitive access control lists and other usage rules, I'll demonstrate the idea with a more playful Minecraft-themed example. So imagine you have 5 pods in your cluster with the following labels. By default, pods have no isolation whatsoever. So in other words, any given pod can access all the other pods and resources in your cluster. There could be many cases where this isn't desired, such as protecting sensitive information stored in a database of some sort, or simply limiting access to specific files. In our Minecraft-themed example, we'll demonstrate the same concept using simple pod labels. So in the Minecraft video game, you don't want entities with hostile intent, such as skeletons or dangerous animals like spiders, to have access to your base. You actually want to protect your base from them. So in pursuing this goal of securing access to our base, we'll be defining a network policy to guarantee that only pods with the friendly label are allowed in. Let's get started by reviewing the YAML file of our Minecraft-themed network policy example. It's a bit longer than our previous two demos, but hopefully pretty simple nonetheless. What I have here is 5 different deployment specs that will create pods with either friendly, hostile, or zombie faction labels. Finally, I also have a network policy spec that will select pods belonging to the friendly faction. This will define an ingress rule such that only pods belonging to the friendly faction are allowed to communicate with each other. After applying the YAML file, you should see 5 pods created for spider, skeleton, player, zombie, and base. Here they are. So right now I didn't apply any network policies, so let's see what happens when we try to access the base pod from our node. Okay, we have access. From this window, I'll be sending a request from the player pod each second to the base pod. Similarly, in this window, I'll be sending a request from the terrifying skeleton pod with definitely less than friendly intentions to the base pod each second. Okay, so as you can see, everything has access to our base pod because it's completely unisolated. Let's see what happens when we apply the network policy. Pay special attention to the timer here that shows when the last output was returned. Okay, I applied the network policy, and as you can see, it immediately kicked in and we're no longer receiving outputs in this window. However, the player pod still has access. Similarly, if we try to access from our node, it should fail. Yeah, we're not getting any output back. Let's see what happens when we disable the network policy again. Okay, I deleted it, so now we should have access again. As you can tell, the network policy is removed again, and so everything has access again. So network policy enforcement on Windows using the Calico Felix host agent process is still in beta, and we're working on improving it. But I hope you can see the potential behind this powerful feature that allows you to set up customized network policies in a granular fashion and very conveniently. This concludes the video. I hope you enjoyed it. Don't hesitate to get in touch if you're interested in trying out some of these features, or ask away if anything else jumps to mind in the comments section below. Thank you.